Okay, so this question is a Newman projection question about 1-bromo-2-methyl propane. It says it wants you to cite down the C1, C2 bond and construct all 6 Newman projections and draw a potential energy surface relating the relative energies of the minima and relating the relative energies of the maxima. So what I tell my students to do is to go ahead and draw all 6 Newman projections that they're going to need in order to do this. And so again, remember, you're going to need 6 of them, 3 minima and 3 maxima. And it's going to go from minima, and the minima are the staggered conformations and the maxima are the eclipse conformations. And it's going to go in order, minima to maxima. And it doesn't actually have to be that order. You can start with a maxima and move to a minima. You can start with eclipsed and moved to a staggered. But it is going to alternate between the two no matter where you start. I'm going to go ahead and label them A, B, C, D, E, and F. That way I can use my the labeling of A, B, C, D, E, and F with my potential energy surface to quickly label the different minima and maxima. Okay, and so it says to start with C1 and C2. The most important thing to do is identify C1 and C2 so that you can correctly build the structure. And so what that means is that this carbon C1 is the same as this one in the middle of the cross of the front of the Newman projection. And this carbon C2 is represented by the big circle in the back. And it's a little bit counterintuitive. Why is the big circle the one in the back? But it just is. And so the red dot is the carbon number 1 and the big circle is carbon number 2. Okay, so let's put everything on the diagram. Now, in this particular structure, we're just at the beginning of Newman structures, so we're not going to give you any information about the 3-dimensional arrangement. So that's not something you have to think about at this point, but you will later. Okay, so what that means is it doesn't matter where you put things on which bond. When you know the 3-dimensional information, that will matter. Okay, so let's take a look. What is attached to that front carbon? Well, that front carbon is attached to a bromine and 2 hydrogens. Now, the thing is that my preference is to rotate the back atom when I'm doing the rotation. So when I do that, now you can choose either one, but the point is that when you choose to pick the front or the back to do the rotation with, stay consistent with that choice. When you're consistent with that choice, you know that you've got the right structure and you've got the right drawing. And the other thing is it makes it easier. Watch what I mean. If I choose to rotate the back, then I don't really have to think about what the front looks like because it looks the same every time. And so for all 6 structures, I can put the Br facing down and the 2 hydrogens facing up. Done. Now comes the hard part, right? The hard part is to make sure that we get the back correct and then do the rotation. And so what is the back connected to? Again, there's no 3-dimensional information, so it doesn't matter where you put things, but it's connected to a hydrogen and 2 methyl groups. Now that I have that particular structure drawn on my piece of paper, everything else does have to be consistent with that. Now, again, I choose by habit to rotate the back carbon. And so I want to make sure that I'm representing that rotation, and I'm going to do it clockwise. So that means the hydrogen moves to the right. The hydrogen moves clockwise, this CH3 moves clockwise, and that CH3 moves clockwise. So at the end of the day, I'm going to have a CH3 here, a hydrogen here, and a CH3 there. I'm going to continue to do that type of rotation. So I'm moving around this way. And so I end up with a CH3 here, a CH3 here, and the hydrogen rotates that way. Now I'm going to continue to do that rotation. So that CH3 there, that hydrogen goes there, and that CH3 goes there. So I end up with CH3, CH3, and H. Continuing with that rotation, moving that H up around there, that CH3 around there, and that CH3 around there, I'm going to end up with CH3, CH3, and H. And one last rotation, then I'll end up with CH3 here, CH3 there, and an H there. So now I've drawn all of my Newman projections. Okay, so the next thing, now that I've drawn the Newman projections, is to examine the structures and to assess them as far as their energies are concerned. And so I'm going to go ahead and I'm going to draw a potential energy surface. And so again, where you start, whether you start with the minima or maxima, or which one you ended up drawing isn't particularly important as long as the relative positions are correct. So I start with A, and I'm going to move to B. And so I always have this starting structure. Everything else is going to be relative. Now, there's some information we can glean from the Newman projections. Specifically, we can compare the minima and decide amongst the minima which are lower energy and which are higher energy. We can also do the same thing for the maxima, which are lower energy and which are higher energy. And so when we lay out the potential energy surface, the choice of the initial spread is somewhat arbitrary. We can move that around, and I can even change the height of it. That doesn't matter. Everything else is going to be relative to those two starting positions. And so let me go back, go ahead and make it out here. And so this will be A and this will be B. Now let's examine then. So I'm going to make all things compared to both A and B. And so let's start off with A. What do I got going on with A? Let me get some things out of the way here. Some things out of the way. And what I want to do is I want to compare A with the next minima, which is C. And so what I want to do is I want to examine the gauche interactions. I want to examine how big groups, big substituents, might be close to each other and causing an increase in strain. And that increase in strain will cause the energy to be higher. If the strain is decreased, then the energy is lower. And so what I see in A is that I have the big group of bromine and methyl interacting with each other there. And I also have the big group of CH3 and bromine interacting on the other side. Now, with C, I still have that interaction between CH3 and Br on the left, but on the right, it's actually something different. It's Br and H. The CH3 is now interacting with some hydrogens. And so those groups that's a small group interacting with a large group. So it's relieved some of the strain. And so what that means is that in relation to A, the minima that is represented by C is lower in energy. Okay, so we know that. All right, so let's do the same thing with the next maxima. We're going to compare the maxima together. I'm looking for information to examine the interactions. So for B, I have a CH3 interacting with a Br, a CH3 interacting with an H, and two hydrogens interacting. Okay, well, I still have the CH3 interacting with an H. Okay, one take only. So no, I didn't just get a phone call and hit pause. But anyway, we were talking about relative energies. And so we were taking a look at B versus D. A lot of times passed for me and no time has passed for you. But we did say, look, we have the same CH3H interaction in both. But the other interactions seem to change. I have bromine no longer interacting with CH3. And so that actually brings a small group and a big group to interact. And so we're reducing the amount of strain. And so the energy of that particular structure goes down compared to B. So I'm going to draw my next maxima for B, C, D at a lower energy level than I did for B. Okay, so let's take a look at the next one because we got to figure out where the next minima goes. And so let's take a look at that. So I have similarly to the first one, I have a CH3 interacting with a Br on the right. And then I have similarly to the one before, I have the CH3 interacting in between two hydrogens. So the only difference between C and E is that they swapped sides of our Newman projection. And for Newman projections, that's the same. And so the energy of E compared to C is the exact same energy level. So the energy level for E is the same as C. And so then let's take a look at the last one so we can get this knocked out. What about the interactions between D and F? Well, I went back, I've got a CH3 and a Br. That was like the first one, B. I've got two hydrogens interacting and then a hydrogen and a CH3. So again, that's just like B, except they flipped sides. And so we know then that the energy for F is the same as the energy for B. And so we needed to draw that maximum there. And then of course, if I go around, then I'm going right back to A. And so there we have it. I've got all 6 Newman projections. I've analyzed all of the different interactions, and I'm able to then place them on a relative potential energy graph. Okay, thanks.